Okay, recording.
Okay. Hello, I'm Dave Chambers. I'm a faculty member at the University of the Pacific. I've helped faculty with their research for years, and one of the common problems that comes up is comparing two different systems for measuring the same thing. Say, two different faculty members looking at a student's work, or digital and analog images, say, of anatomical landmarks. There's three sources of variation that you're measuring when you do those comparisons. One is the actual effect. Are bigger things bigger on both systems, smaller things smaller, and so forth. The second is random variation. Sometimes it just happens that something is a little bigger in one rating system, and then it's a little smaller the next time you look at it, and so forth. That can be taken care of by increasing the sample size. The bigger the sample, the more that random variation just cancels itself out. The third source of variation is bias. That means that there's something systematically in one of the situations is causing it to be a little bigger than the other or a little smaller than the other. The problem with bias is, first of all, most people aren't aware that it exists. Second of all, a large sample size doesn't take care of bias. If you get cheated every day when you go to the supermarket, you're going to still get cheated every time. Doesn't matter how often you go. Now, let's take a look at how we can measure random variation and bias. They use different methods for separating those two out. I have some data here. If you look at the screen, I just called one of them arbitrarily X and the other one arbitrarily Y. The first line shows two different measurements of the same thing, say anatomical landmarks. Y said it was a 1, X said it was 1 and Y said it was a 2. And down here, X said it was a 5 and Y said it was a 5. And if you go all the way down here, you got a big one, 13 and 11. So it looks like the little numbers are going with the little numbers and the big numbers are going with the big ones. Let's check that out in the standard approach using, this is just an Excel spreadsheet. And what I want to do is highlight, those two numbers. Like that. I've just highlighted that whole set. Then I want to go up here on the top line where it says insert. I want to click there. And then I want to go over here where it shows me that I can draw different kinds of pictures of that data. I'm picking the scattergram. And I'm going to pick the first one since that's the easy one. Click it and there it is. It's done all the graphing for me. And as you can see, that big number, 13, goes with the big one over here, number 11. The little one, number 1, goes with the little one, number 2. And the line is nice and flat. This is a correlation analysis, and since the numbers are close to being flat, we know there's a high correlation. In other words, there's not a lot of random variation in the sample. Now, how much random variation? That's easy enough to calculate. Put the cursor on one of the dots, any one of them, it doesn't matter, and right-click. That's not the normal way of clicking, it's on the other side. Just right-click, and it gives you a screen of hidden options. Incidentally, when you don't know what to do with the computer, right-click, it helps a lot. Go down here where it says add a trend line, and it tells you all kinds of things you can do. You can do exponential curves, you can change the colors, you can do all sorts of things. We only want the last two items, which say display the equation and show the R-squared value. Choose that, and it's added something here, and it always puts it in the wrong place, so move it over. And that shows you that the correlation is very high. This is R squared. You can get R simply by taking the square root. And that number is close to 1, the maximum. That means that these numbers here are very close to the trend line. In other words, the correlation is very high, so the amount of random variation is very small. Now, what about bias? What you've actually done here is calculate both a correlation coefficient and a regression line. Remember, this line is called a regression line. What you want to show that there's no bias is that the change in one measurement is the same order of magnitude as the change in the other measurement. If you go up one on this one, you want to go up one on the other one. If you go up 5 on X, you want to go up 5 on Y. In other words, every change in one measure is reflected exactly the same on the other measure. If that's true, the slope of the regression line is a perfect 45-degree angle, and that shows up statistically as a correlation, a slope line of 1.000. This number, you can see, is less than 1. It's 0.75. That means for every 1 you go over on the X, you only go up 3/4 on the Y. That means X always overestimates Y in this particular example. That's something that you want to be aware of because it's bias. It would mean that if you use one of the systems, you get a different answer from if you use the other. This is a very common sort of occurrence where there's judgment involved. The reason is that when people make judgments, they are too conservative. They underestimate the top, which brings the line down on the right-hand side. They underestimate the bottom, which brings the line up on the bottom side, on the low end, and the line gets flat instead of being a perfect 90-degree angle. So what I've shown you is a very easy way of calculating the correlation to measure random variation and the regression line to measure systematic bias. And that's it.